Hello, my name is Darren Thomas and I'm the Director of Educational Research Techniques. In this video, we're going to be taking a look at a periodic function. In particular, we're going to be taking a look at the tangent function. So let's go ahead and get started. So you can see on your screen right here, this is a picture of a tangent function. Obviously, it looks very, very different from what we've talked about in the past when we looked at the sine function and the cosine function. So, you know, the sine function or the cosine function, it kind of behaves more like this. Again, obviously this is not drawn to scale because that's just not what I do. But you get the idea here. It kind of moves up and down like this. But the tangent function is very, very different. It goes up and it disappears, and then it comes down, and then it goes up and it disappears. There's something weird going on here that makes this behave much differently. So why don't I start by drawing the basic tangent function for you, what it looks like in terms of all the different terms. It's very similar to the, the sine function. So we start, here's the terms. We have a, then we have tangent, and then inside that we have the quantity of b times x minus c, and then outside that plus d. These are all the different pieces of the tangent function, and of course all this should look familiar because it's just like the sine function, except the function here, the tan, was different. Now, as you can see here, the first term is the a term, which is normally refers to the the amplitude. However, if you notice carefully here, there is no amplitude because of the strange behavior, which I'll discuss in a second. So normally when we talk about this a term, it's called more of a stretching compressing factor. That's kind of the, the stretching or compressing factor. That's what this first term is here. All right. So that's what it does. It stretches or compresses the behavior of the tangent function in terms of, like, you know, how wide or how compressed that S shape is. The B term is used, of course, for calculating the period as before, except now the formula is different. You do pi over the absolute value of b rather than 2 pi. Again, we'll get to that in a second. And then the C here is your phase shift, the horizontal phase shift, and then the D is kind of like used for, you know, moving it up and down vertically. So again, very, very similar. Now back to this unusual behavior where we have this disappearing loop here. As you may remember, if not, we'll remind you right now, tangent is basically calculated by using sine over cosine. All right. Now here's the thing. This graph disappears at pi over 2 every single time, and that's because if you calculate cosine and you put pi over 2 in there, you will get 0. And of course, if this denominator becomes 0, you have a problem. You cannot divide something by 0, so you get undefined. This is why the graph disappears. So you constantly have this problem over and over again. And so this is why you get this disappearing function. And so what's happening is that essentially wherever you're at pi over 2 on the graph here, you got what we call these, they call asymptotes. I don't know if I'm saying the word asymptotes. They're kind of, that's what they're called. Forgive the mispronunciation. And asymptote or asymptote is where a line that a curve approaches, you know, infinity, it gets close, but it never touches it. So you can see here, as it goes up, it gets close to pi over 2, but it never touches it. And then the same thing down here, it goes close. And then when we say pi over 2, it can also be 3 pi over, whenever you add 3 pi over 2, 5 pi over 2, you know, negative pi over 2, negative 3 pi over 2, etc. All those are examples there where you're going to have this problem. And so this is why it keeps repeating over and over again, because pi over 2 apart, they're always going to keep showing up. And so that's why. And so what's happening here is that you have something where where it's available, then it's not. Available, then it's not. And the analogy that the book I read about this gives you is that it's kind of like when you have the flashing light of a siren. So have you ever seen like a siren on a police car? You know, first you see it, then it's gone. And then you see it again and it's gone. And then you see it again and it's gone, like that. And it's periodic. In other words, it's very, very at specific intervals. You can see it and see it and see it. That's what's kind of happening there. And so this is what this tangent function is capturing, that kind of a behavior where something is available for a period of time and then it's not. It's available for a period of time and it's not, etc., etc. So having explained that as clearly as we possibly could, why don't we move on to some examples of different you call them different tangent functions by manipulating these different a, b, c, and d terms here. That's what we're going to do. So the black line, if you can't see that, is the regular tangent function. So just tan x. That's it. No a, b, c, d manipulation. Now the green line is where we manipulate the a term. 3 tan x. That's what we have here. So there's no manipulation of c and d. And so you can see that we kind of lose some of that S shape and it becomes a little bit more linear. But of course, it's not linear. But you can see that it becomes a little bit more linear in terms of its behavior. And this is what happened, is that it's kind of it's kind of compressing it, if you will. Not stretching it, but compressing it. And so it takes on more of a linear shape. And so the blue line here is -1/3 tan x. And so you can see here now that the S shape is spread out more. And the reason this is looped to the left now is that because we put the negative sign there. So you can see how the A term, how it affects things. All right, let me get this off here. Sorry about that. Now here, again, the black line is the traditional tangent tan x with no manipulation. But the red line here, we're manipulating the B term now. So the red line, the red line is tan 1/3 x, like so. And so you can see how it really got stretched out quite a bit here. You know, it's really got that long looping S shape now, and it's, you know, really looking quite different. Now, in terms of this dark yellow term, this is just tan -1x, or your tan -x, if you will. And so we just flip the sign, but it's basically the same behavior, if you will. Not a whole lot of manipulation there. Okay, let's move on. I think I did that one. All right, here we go. And so now we're going to look at manipulating the C and the D term. So for the gray, what we have here is we have tangent of x minus 1. And so you can see, compared to the black line, which is the regular tangent function, this shifted it to the right 1 unit. That's all that did. And of course, for the purple, you have now tan x, but then outside the parentheses, plus 1. And you can see that just moved it up 1 unit. And so that's kind of how it changes the behavior. Now, there are other things that you can calculate. For example, you can calculate the period. The equation for that, we're not going to really do it here, but it's going to be P equals pi over the absolute value of B. So in this particular example, the period is going to be pi, because we got, 1B, absolute value. That's all it is. It's going to be pi in this particular situation. That's the period. And so you can see how it moves every period like that. All right, so it's not that deep. But that's essentially kind of an overview of the behavior of the tangent function. So let me just kind of wrap up and summarize things, and we'll conclude the video. So in this video, we took a look at the tangent function and some of the unique characteristics of it. First of all, it doesn't behave quite like the sine function at all, because it's because it has those asymptotes, if you will, that are because when you do sine over cosine, which is what the tangent function is, cosine with the quantity of pi over 2 inside the function comes to 0, and you can't divide by 0. That's why you don't have the nice beautiful wave of the sine function. And so, having said that, we also took a look at the different components of it, and this is the actual equation right here and how it behaves. And then we went through some examples manipulating these different potential constants. So this example here, these two examples, the blue and the green, are manipulations of the A term, which would be called the amplitude when we're doing sine and cosine, but here it's like a stretching compressing factor. Here is some manipulations of the B term. Again, with the B term is used for trying to calculate the period, and you can see here how it's manipulated. This also right here is the gray is the manipulation of the C term, and so that moves it to the left and to the right, and the purple is the manipulation of the D term, which moves it up or down. And so that's kind of how the sine function, or excuse me, the tangent function works here. So I hope that this video was clear. You were able to understand the concepts that were talked about here. I know that it can be a little difficult at times, but reviewing it over many times and it'll start to make sense. So My name is Derek Thomas. I am the Director of Educational Research Techniques. Take care.